Hello everyone, my name is Mohammed Shahzad. I'm from Monash University, Australia. The topic of my presentation today is quadrant analysis of zero and adverse pressure gradient turbulent boundary layers using high spatial resolution two-component two-dimensional PIV measurements. I'm thankful to the PIV for sponsoring my research and Australian Research Council for their grant and the co-authors of this for their contributions to this research. Reynolds shear stress measurement in wall bottom turbulence is important as it contributes to the turbulence production. It is worthwhile to quantify the contributions of positive and negative velocity fluctuations to the mean Reynolds shear stress and their effect on the turbulence production. Quadrant analysis of Wallace et al. Separates the UV events into four categories called quadrants, which help us investigate the contributions of each quadrant motions, especially the ejections and sweeps, to the Reynolds shear stress and turbulence production. POD is used as a filter in order to select the most energetic structures and leave aside the non-coherent turbulent part. The PIV snapshots are stacked into the matrix form, which is then decomposed into the POD spatial modes and their temporal coefficients using singular value decomposition. A number of POD modes that contain energy approximately equal to the total energy is then found. Then streamwise and wall normal velocity fluctuations are reconstructed from the POD field. Then the quadrant method is implemented to try to elucidate the turbulent events present in the flow. Why are we using these fluctuations which are reconstructed from the POD? Because with the fluctuations from full data field, features near the wall are masked and the profiles of the quadrant contributions are not smooth in the outer region because of the less number of samples in the conditional averaging. POD removes these artifacts and gives a better estimate of the contributions. High spatial resolution PIV images were taken in LMFL wind tunnel, Lille France. The zero pressure gradient measurements were taken at 6.8 meter downstream the tip wire, and the adverse pressure gradient measurements were taken at s equal to 5.6 meter, where s is the curvilinear coordinate along the ramp. The PIV data has been analyzed with an in-house multigrid multipass digital PIV code. These measurements are taken in the same conditions as in EU-HIT experiment of Cuvier et al. 2017. The current measurements have considerably higher spatial resolution than EU-HIT measurements. All measurements have an inflow velocity of 9 meters per second. The adverse pressure gradient measurements are at beta equal to 2.27, where beta is a Clauser's pressure gradient parameter. The EU-HIT measurements cover the outer region of the boundary layer, while the present high spatial resolution measurements resolve further down to the wall. With the high resolution, we are highlighting the improved measurements of velocity fluctuations. The present measurements are consistent with the EU-HIT measurements as shown in the figures of the first order and second order statistics. High spatial resolution measurements cover from wall to the beginning of the wake region only. The quadrant analysis using POD will be limited to the high spatial resolution measurements only. The fractional contribution and the cumulative fractional contribution of the POD modes is shown in this slide. The first mode contains nearly 32% of energy in ZPG and 43% in APG. For reconstruction of the velocity fluctuations, we need to use R number of modes which contain 99% of the total turbulent kinetic energy. R is 1500 for ZPG and 1200 for APG. We use these many modes so that the contributions of the small scales near the wall are not neglected. In order to further verify the correct selection of R, we look at the quadrant portions with changing R values. For R equal to 1, the first mode mostly contains the second and the fourth quadrant motions only. The percent Portions of the second and fourth quadrants keep on decreasing, and those of the first and third quadrants keep on increasing with increasing R values until they become asymptotic beyond the selected values of R for both boundary layers. The Reynolds shear stress profiles from the POD decomposed field using R equal to 1500 for ZPG and 1200 for APG match exactly with those from the full data field all the way to the wall. This means that the contributions of the small scales near the wall from the POD reconstruction are likely to be captured and not neglected. In ZPG-TBL, very close to the wall for Y plus less than 15, fourth quadrant contributes considerably more to the Reynolds shear stress than second quadrant, whereas farther from the wall, opposite is the case. Above Y plus equal to 50, contributions of both ejections and sweeps are nearly constant. In the same region, the first and third quadrants have similar contributions, which are nearly 50% in intensity as compared to the fourth quadrant, but with opposite sign. In APG-TBL, contributions of the second and the third quadrant motions are almost similar to their counterparts in ZPG-TBL, but they are slightly more intense near the wall. Contrary to ZPG-TBL, fourth quadrant contributes more to the Reynolds shear stress than the second quadrant from wall to the beginning of the wake region in APG-TBL. Similarly, first quadrant contributes more than the third quadrant in the same region. As contributions of both the first and the fourth quadrants are amplified in APG, the increase in the fourth quadrant contribution is larger than in the first quadrant, and this shows that the outer peak in the Reynolds shear stress profile is formed due to energization of sweep motions of high momentum fluid in the outer region of the boundary layer. Here we look at the contributions of the quadrants to the dominant term of the turbulence production. Near the wall, sweeps are the main source of the turbulence production, followed by the ejections. These contributions are amplified in APG, but they are still in the same order. Contributions of the first and third quadrants are negative. In the outer region, the contributions of the second and the fourth quadrants, as well as the first and third quadrants, are nearly the same. This brings me to the conclusion slide. Very close to the wall, sweeps contribute considerably more to the Reynolds shear stress than ejections. Farther from the wall, the opposite is the case in ZPG-TBL, but not in APG-TBL, where sweeps contribute always more than the ejections. Above Y plus equal to 50, contributions of all quadrants remain almost constant till beginning of the wake region in both boundary layers. The first and the fourth quadrant contributions are amplified by APG, but increase in the fourth quadrant contribution is larger in magnitude, which is the main reason of the outer peak in the Reynolds shear stress profile. Near the wall, the sweeps contribute more to the turbulence production than ejections. These contributions are amplified in APG, but they remain in the same order. Thank you very much for listening.